Thank you and good evening. Today I'm presenting our work on adaptive management framework to improve fishway performance. This study conducted by the GEA group focuses on how technology and real-time data can help us overcome the limitation of traditional static river management. River fragmentation is a critical threat to aquatic biodiversity. The main issue is that most fishways are designed as static structures. We build them based on theoretical conditions and then we forget them, the build and forget approach. But rivers are dynamic, and these structures often fail because they cannot adapt to environmental variability. We conducted our research at the Duero River in Vado Condes in Burgos. We work at the runoff river plant with a 3.75 meters head. This is a perfect case study because the plant's operation directly affects the water levels available for our target species, that is the Iberian barbel. And to monitor the site, we deployed a low-cost IoT sensor network. First of all, we installed water level sensors to track real-time hydraulic conditions. For biological tracking, we use infrared fish counters and pit tag antennas. We tag over 1,100 fish to verify complete access through the fishway. Here, a multi-parametric probe was added to record environmental triggers like temperature and luminosity. And all sensors are connected via hybrid radio and cable infrastructure. And the brain of the system is a Raspberry Pi running Python algorithms. And data is sent to the cloud via satellite or GSM, allowing for remote and real-time management. Our methodology merges hydraulic, climatic, and biological records. We use edge computing for real-time data cleaning. The core of our analysis is a random forest model developed through recursive feature elimination supported by neural networks for autonomous event classification. Moving into our results, the random forest model achieved a high accuracy. As shown in the future important chart, we categorize the variables into two groups, climatic and hydraulic. This distinction is fundamental to understanding how the fishway performs. On this graph, we can see the role of the environmental factors. These act as triggers that determine when the migration happens. Factors like luminosity and water temperature, that here, create the biological seasonal window, shown here by the Gaussian curve. This curve represents the period when fish are biologically motivated to move based on external cues. However, in this graph, reveals the critical impact of hydraulic regulators. While the climate triggers, the blue line, define the potential timing, the actual variation and magnitude of passive succeed depends on the hydraulics. Now, how do we translate this model into a practical tool? So, this slide shows our predictive adaptive framework. First, we use forecasting, feeding environmental predictions into our model to estimate future performance. Then, our recursive optimization algorithm calculates the optimal values for the variables can actually control, like the water levels and sluice gate position. And finally, the system is self-learning, ensuring that the model adapts for long-term environmental shifts and climate evolution. The most practical application is regulating the sluice gate. As you can see in the graph, by reducing the hydraulic drop at the fishway exit, we found the potential 166% increase in fish passage efficiency. And crucially, this optimization does not require altering the hydropower plant's energy production. That is an important point for economic. And in conclusion, real-time hydraulic regulation is the missing link in fish waste design. Our approach is affordable and scalable using IoT sensors, and by managing operation during peak biological windows, we can reconcile energy and ecology, meeting EU Biodiversity 2030 targets. Thank you.